In the earlier class, we defined two new information measures. This were joint information measure and the other was conditional information measure. Joint information measure was given as h of x y I is equal to 1 to n, j is equal to 1 to m. This was the joint information measure which we define when we have two events taking place simultaneously and we observe them as one. Another information measure which we defined was the conditional information measure, and that was defined as h of y given x was equal to minus summation over xi yj log of probability j is equal to 1 to m. This is the conditional information measure with regard to experiment y given x, and similarly we can define h of x given y. Let us look into the properties of h y given x little more into depth before we proceed ahead. So, the two important properties of h y given x would be, one property is h y given x is always greater than or equal to 0, and the other property is that h of y given x is always less than or equal to h of y, with equality if and only if x and y are statistically independent. Let us try to prove these two properties pertaining to h of y given x. Now, to prove this property, the first property, it is not very difficult. So, proof, the first one we have to prove is h of y given x is always greater than or equal to 0. Now, because probability of yj given xi is less than or equal to 1 for all I and j, therefore, this implies that minus log of probability yj given xi is always greater than or equal to 0, and so from the definition of h y x, which is nothing but summation over probability of xi yj log probability of yj given xi, this quantity is positive, this quantity is positive. So, for totally this quantity is always greater than or equal to 0. So, the first property has been proved. Now, to prove the second property, that is h of y given x is always less than or equal to h of y, it is not very difficult. We write off equation minus h y is equal to minus summation over probability of xi yj log of p of yj given xi minus hy is probability of yj log probability of j is equal to 1 to m, here also j is equal to 1 to m, I is equal to 1 to m. Now, this is very simply can be written as this quantity out here, summation j equal to 1 to m p y j, can be substituted by double summation, and once you rule that double summation, this expression can be written as this. Now, we also have seen that log x is always less than or equal to x minus 1. If I use this property, then I can write this expression out here, x is equivalent to this quantity out here, then I can write that h of y given minus h of y is always less than or equal to double summation probability of xi j probability of yj I is equal to 1 to n, j is equal to 1 to m, multiplied by, because this expression is with respect to natural base, whereas we have here log to the base 2. Therefore, when we convert from log to the base 2 to the log to the base e, we will get this factor out here. Now, this can be simply simplified as minus double summation of this whole thing gets multiplied by log to the e. Now, writing this expression using the Bayes theorem, we will get summation of probability of xi, probability of vj, yj minus probability of xi yj I is equal to 1 to n, j is equal to 1 to m. Similarly, I will have I is equal to 1 to n to 1 to m. Now, these summations are 1 minus 1 and this is equal to 0. Therefore, what we get is h of y given x is always less than or equal to h of y. What this expression says is that the uncertainty which is there in the event y or experiment y after the event x has been observed will be always less than the uncertainty which is there initially when I do not observe x. Correct? So, when I have the foreknowledge about the event x, the uncertainty about the event y will be always less than the uncertainty of the event y when I do not observe event x. And therefore, the information of h y given x will be always less than or equal to h of y. Now, let us have a look at the relationships between the joint information, conditional information measures and the marginal information. So, I want to find out the relationship. This is my joint information. I have my marginal information measure, and then I have my conditional information measure. Now, I want to find out a relationship between these three quantities. Now, we will show very shortly that h of x given y is nothing but equal to h x plus h of x given y, or I can also write this h of y plus h of y given x. So, this is another important relationship which we will be using during the course of our lecture today. So, let us try to prove this relationship. Let us try to prove the first relationship. Let us look at a definition of h of x given y, which started in the morning. So, this is nothing but probability of xi j log of p of xi yj. So, let us start with hxy, which by definition is given by this term expression. So, this if I simplify it, I can write it as probability of xi yj log of p of xi probability of yj given xi. This I am writing using the Bayes rule. So, I is equal to 1 to n, j is equal to 1 to m, and this I can simplify as probability of xi yj log of p of xi minus summation, double summations probability of xi yj log of probability of yj given xi. I is equal to 1 to n, j is equal to 1 to m, and similarly out here. Now, this quantity out here is nothing but your hx, and this quantity is nothing but by definition hy given x. Sorry, this quantity out here should not be hx given y, but should be h of y given x, and similarly this quantity should be h of x given y, correct. So, finally I get the joint information which I get from two events x and y is equal to the information which I get from the event x alone plus the information, additional information which I will get from event y after the event x has occurred. So, similarly I can show that this is nothing but h of y plus h of x given y. Now, h of x given y is this quantity out here. If you look at h of xy is equal to h of x plus h of y given x. We just proved that this quantity is always less than the information in y alone. So, this quantity out here will be always less than hx plus h of y. So, the joint information in x and y is always less than the sum of the information in x and y, and they are only equal when x and y are independent. With this little background, we will move ahead where we had left last time, and we were studying the properties of a Markov source. So, let me revisit the Markov source and let us look at depth into the properties of this Markov source. So, I start again with the first order Markov process. So, first order Markov source will have its source alphabet, let me assume as S1, S2 up to SQ. The size of the alphabet of this source is Q, and this is the first order Markov source. What I mean by first order Markov source is that the occurrence of any particular symbol will be dependent upon the occurrence of the previous symbol. That is what we mean by the first order Markov source. Let me assume that I have a time instant t1. At this time instant t1, let us assume some symbol occurs at this time instant 1, and let us call that symbol which occurs is I. So, S1I is one of the symbols from this source alphabet, and let me assume that I have another time instance t2, and at that instant another symbol occurs at time instant t2, and let us call it S2j. So, S2j is again one of the symbols from this source alphabet. Now, if I were to find out what is the information which I gain when I transit from S1I to S2j, then to find out that information I will require the conditional probabilities of S2j given S1I. So, if I have this conditional probabilities available, then I can calculate what is the information which I get when I transit from S1I to S2j. Now, considering the time instances t1 and time instant t2 as two different experiments which are related to x and y, similar to what we define hyx, we can define the information which I get, additional information which I get when I transit from S1I to S2j. So, that is very easy to calculate, and I can say that h of S2 to S1 would be given by this expression. So, this is the amount of information which I get when there is an arbitrary transition from one state to another state. In the light of what we have done earlier with relation to the experiment x and y, I can write that the additional amount of information which I get for an arbitrary transition like this from t1 to t2 is given by this expression out here, correct. So, if I were to find out what is the joint information between S2 and S1, we can find out very easily as h of S1, S2. This is the joint information which I will get from messages of length 2 would be I is equal to 1 to q, j is equal to 1 to q, probability of S1I S2j log of probability of S1I S2j. Now, this can be easily shown to be as H of S1 plus H of S2 given S1. This relationship we have just seen. Instead of S1 and S2, we had seen in terms of X and Y. So, it is not very difficult to derive this relationship. Now, we have also seen that because H of S2 given S1 is always less than equal to H of S1, therefore, H of S1 S2 is always less than equal to H of S1. This quantity out here should be H of S2 is this. So, H of S1 S2 is always less than or equal to H of HS1 plus HS2, which we have derived, and if you assume that Markov process is stationary and ergodic, then H of S1 is equal to H of S2 is equal to H of S, and therefore, H of S1 S2 will be always less than or equal to twice of H of S. So, what we have derived now is that when I look at the entropy of messages which are of length 2 symbols, and these symbols come from a Markov process of a first order, then the total information in the messages of symbols of length 2 turns out to be less than or equal to twice of H of S, HS, correct. Now, if this Markov process of 0 order, then I would have got is equal to twice of H S. So, the conclusion is that whenever there is a dependency among the symbols, then the messages of length L, the total information will be there in that will be always less than equal to L times the entropy of the source. We had seen this result earlier, where we had proved that if the symbols are independent, then H of S1 S2 turns out to be twice HS. Now, this we have proved it for the first order Markov process. Now, let us move to some higher order Markov process, and let us make the things little more generic. So, I will consider Markov source of order k which is greater than 1, and at the moment I am interested in the occurrence of a particular symbol at the time instant, say capital N. So, let me say that the symbol which occurs at a time instant capital N, let me denote it as Sn, and if I assume that this symbol which occurs from the source S is coming from a Markov process, then what I am interested in the additional information, the average additional information which I get on the occurrence of a symbol at a time instant Sn, given that I have observed all the preceding symbols right from time instant 1 up to time instant n minus 1. So, if I use the general properties of entropy, then I can define the average additional information which I am going to get on the observation of Sn, having observed the preceding symbols, will be nothing but this quantity Sn minus 1, Sn minus 2, this will continue up to right. So, this is the additional information which I get when I observe symbol Sn at time instant n. Now, this quantity I will define it to be as, by definition I will call it as Fn of S. Now, before we go ahead, there are some interesting properties of this Fns. One interesting property would be that H of Sn given S of n minus 1, n minus 2, S2, S1 is always less than equal to H of Sn given Sn minus 1, Sn minus 2 up to S2. Now, it is not very difficult to prove this. Intuitively it is very satisfying that the occurrence of S1 cannot increase the uncertainty of the occurrence of Sn. So, what this implies, this relationship implies is that okay. What this relationship implies is that that knowledge that is delivered by the first symbol S1 cannot lead to an increase in the uncertainty about the nth symbol, but it will always decrease or leave it unchanged. So, this is the significance of this expression. Now, there is a very important theorem which we will try to derive from this. The theorem says the conditional amount of information that is Fn S, which is by definition equal to H of Sn given Sn minus 1 up to S1 of the nth symbol in the case where the preceding n minus 1 symbols are known is a monotonic decreasing function of n. What we mean by that is h of Sn given n minus 1 preceding symbols will be always less than equal to h of Sn minus 1 given Sn minus 2 to Sn 1, and this way we can so this is a very important theorem which is associated with a general Markov process. So this is what we had defined as an additional information which I get on the occurrence of the nth symbol when I know the preceding n minus 1 symbol. So what it says that the information which I get from here will be always less than or equal to the information which I get when I go back to the time instant n minus 1 and I observe the symbol, and given that at that time instance n minus 2 preceding symbols have been observed, and if I continue like this, finally I land up with the first symbol. So the uncertainty which I have when I observe the first symbol is the maximum compared to the uncertainty which I have at the nth instant of time. We will try to prove this theorem. So let us look into the proof of this theorem. Since the source, the Markov source which we are considering is stationary, the source is stationary, the conditional amount of information are independent of the position of the nth symbol in the sequence of source symbols which are being emitted. So what it means is that h of Sn minus 1 given Sn minus 2 S1 is equal to h of Sn given S of n minus 1, but this will go up to S2. I can write this expression because the source is stationary, and we have just seen that the property of a Markov source is conditional information will be always, this will be always less than the quantity on the right hand side. This I can write because the source is stationary, and this is the property of the additional information measure, and from this too it directly follows that h of Sn given Sn minus 1 up to S1 is less than equal to h of Sn minus 1 given Sn minus 2. So, using these two properties I get this. So, this is by definition nothing but Fn of S is less than equal to f of n minus 1 S. So, similarly I can extend h of Sn minus 1 given Sn minus 2 S1 is less than equal to h of Sn minus 2 given Sn minus 3 up to Sn1. So, I can extend like this and simply show that this condition is true. Now, what it follows that as I keep on increasing n, the value of Fns keeps on decreasing. Now, since Fns is always greater than or equal to 0, what this implies is that limit of n tending to infinity of Fns should converge, and let me call that limit as by definition h infinity s, and this is nothing but limit of n tending to infinity of additional information of Sn given n minus 1 preceding symbols have been observed. This is bits per symbol, and from this expression out here, because this is expression from these two expressions, I can write 0 is greater than this expression is F1 S. Now, this quantity out here, the quantity which I get when n tends to infinity of Fns is by definition is known as, this quantity is the amount of information of a discrete information source with memory. So, now we have formally defined the information measure for a Markov source with memory. We have considered the value of k to be arbitrary. The k stands for the order of the Markov process. So, what we get is that if I want to calculate the entropy of a Markov process, then entropy of the Markov process is nothing but limit n tending to infinity of Fn s, and that is nothing by definition limit n tending to infinity the additional amount of information. So, this by definition is the definition for the information measure of a Markov source with memory. Now, if we assume a Markov source of order k, then what this implies is that as I keep on increasing the value of n, beyond certain value of n, this Fns will not fall. This is very easy to appreciate because probability of Sn given Sn minus 1 up to S1 will be equal to probability of Sn given Sn minus 1 up to Sn minus k when the Markov source is of a kth order, and if this relationship is valid, then h of Sn given Sn minus 1 up to S1 would be equal to h of Sn given Sn minus 1 up to Sn minus k, because only k preceding symbols will come into picture, and because the Markov source is ergodic and stationary, I can write this as h of s k plus 1 given s of k minus 1 up to S1. So, for a Markov source of order k, h infinity s will be equal to nothing but f of k plus 1 s is equal to this quantity, because for n beyond k plus 1, for n beyond k plus 1, this quantity will remain constant and it will not go lower than this value, and then I can write h infinity s is equal to this value. For 0 memory source, k is equal to 0, and in that case h infinity s is nothing but h of s. So far we have considered the messages with symbol length of unity. Now the next question is, like we had done earlier, if I look at messages of length other than 1, then what happens to the entropy of those messages? Let us look into that. So, let us assume that I have a message V which is composed of n symbols of this Markov process. So, I have S1, Si1, Si2 up to Sin, capital N. So, what I do basically is that I assume that I have messages now of n symbols, capital N. I have the messages of n symbol. Now, if I look at these messages and if I were to find out the entropy of this, then how this entropy is related to my original entropy. Let us analyze this. So, if I want to calculate the entropy of this, then I can write entropy of HV is nothing but H of S1, S2 to HSN. So, this is the information which I get from messages of symbols consisting of length n, capital N. Now, if I define another quantity as average information per symbol, which is by definition equal to 1 by n of HV. So, this is my average information which I get per symbol. So, this is equal to 1 by n H of S1, S2 to N. This will be bits per symbol. Now obviously the symbols are statistically independent, then H of Hn would be nothing but summation of H of Si. This expression I can write for this provided my symbols in this message of symbol length n are independent, and in that case I can simplify this to be as H of S. Now if the symbols are dependent, then I cannot write like this, and then I can go to a more fundamental definition. I can say that HNS is equal to 1 by n, and this information out here, joint information in n symbols, can be written as HS1 plus H of S2 given S1 plus H of Sn given Sn minus 1 up to S1, and this is equal to 1 upon n times so this I get an average information per symbol, and that is related to 1 by n summation of Fj S. Now as was the case for Fn S, we can similarly show that H of n S is a monotonic decreasing function of n, and it will be interesting to find out that the limiting value of HNS turns out to be the same as the limiting value of Fns. The limiting value of Fns, we have seen it was H infinity S, and this was the entropy of a Markov, so that is what we have defined. Now we can also show that the limiting value of HNS as n tends to infinity also turns out to be H infinity S. We will try to prove this in the next lecture.